So the for loops, they are also in the videos that you will be seeing in the upcoming, in the upcoming weeks. But as I introduced for loops on Tuesday, even just for a brief kind of, this is what it does, not how it works, but this is what it does. It's worth introducing it multiple times as though you hadn't seen it before, because for loops I find is the part where most beginners tend to struggle, because it involves you having to not just read, but also understand what's going on. It's not, especially as, the numbers change. We'll also be discussing a brief history of pi. Yeah, you wouldn't think a number has history to it, but pi does have history in the sense that it is an approximation. And calculating such approximations has gone through a lot of different iterations. So first and foremost, let's talk about for loops. So I will share my screen for those of you who are online. And again, if you just don't feel like you can go to class because you are feeling ill or the like, then just simply drop online, send me an email and saying, hey, I'm going to be attending online today. Don't even have to tell me why. Okay, because I'll assume, if you don't tell me why, I'll just assume you're sick or not feeling great. Okay. So I've opened up idle and I've opened up our file over here, and then I just have to check one thing, which is well, I have to check two things. First off, those of you in the back, can you see me? Can you see what I wrote? Must you strain your eyes to read it? No. Okay. So that is good. That is, if you need me to adjust the font size, please let me know. All right. So let's talk about for loops first and foremost. All programs basically are made up of, pi and 4. Okay. So most programs are made up of basically, most programs, pretty much actually all programs are made up of some combination of 3 statements. Imperative statements, which you can remember by imperative imperial, meaning command, meaning there's some kind of authority. Those are things you've been doing so far, like print. When you say print hello. Okay, and let me just see what's in the chat. Yeah, I'll always be booting up the Zoom link. It just makes it easier to deal with because there's almost always going to be somebody out. So print hello, that's it, which will do that. It will print hello. All right. So conditional statements just do what you say. There are also statements that the second type of statements are statements we call conditional statements, which we'll be learning later in the semester. But those are your if-else statements. So if condition, where condition is some variable, do this, else do that. That is the second type of statement that we will be introducing later in the semester. It's conditional, meaning it can go some way or the other way. It's where you have if you're making a flow chart, this is where you make a decision, right? Are you going to go to the left? Are you going to go to the right? Are you going to pick something up or are you going to put something down, right? So that's the second type. The third type is the repetitive statement or the iterative statement. Repetitive meaning repeating, iterative meaning going through something, iterating through something. We'll use that term a lot, iterating, because that is the way that Python decides to do things. So I've written this hello, and if I wanted to repeat it, I can use a for loop. If I want to repeat it 5 times, I would say for I in range, and this I could be any variable. I could even leave it as an underscore to me, which you use when you say, I don't care what that variable is, which I don't in this case. In range 5. All right. And that is the form. If the kata, if you're coming from martial arts, which basically looks like that says, hey, I'm going to go ahead and repeat this statement a certain number of times. Got it? So this will repeat it 5 times. But there's more power to be had with the statement. There's actually a considerable more power to be had in this statement, which is like I've been mentioning that there's a variable here, I, right? There's this variable I. So why? And the answer is so that it can change value. The variable can vary in value. I know I should always avoid annoying alliteration, but I just can't help myself sometimes. All right, so instead of printing out hello, and remember the output is just being dropped over here. Instead of printing out hello, I'm going to try printing out the variable I, not the string I, because this would mean if I did this, it would mean literally print out I, but the variable I. And by printing out that variable, Python will go, okay, you want to print out I. Well, in order to do that, I've got to see what's inside of it. And sorry, cancel. There we go. And it prints out 0, 2, 3, 4, which will be completely surprising to every one of you unless you've done programming before. So don't feel, so if this makes no sense, don't worry. Okay, just looking for my amazing magic pen. It should be here somewhere. Candy, candy, more candy. Did I leave it upstairs? Annoying if I did so. Inconvenient. That thing is. Annoying if I did so, but also not a deal breaker. My handwriting, as you have seen, is quite terrible to begin with, so no great loss there. When we create this range 5, we're actually creating a range. And one of the things I love about Python is that you can print out pretty much anything. For instance, I could print out print. Now notice here at this top point, what's going on inside the parentheses. So print is a built-in command. When you have a command, a verb, a function in Python, you invoke it, which is, you know, that magic word that actually means to make into being. This actually makes it the print function saying to run. That's what the parentheses do. It invokes it. It says, I want to execute it. But I can actually do whatever I want with it. I can say, hey, print the print function, and says, hey, we've got a built-in function called print. I could even rename it in a way, or give it a second name by saying say is equal to print. You can store anything you want in a variable in Python. It's kind of crazy. This is getting beyond the scope, but I can just simply watch. Say. So I just gave it a new name, and I just simply call it say hello. This should work. Yeah, totally works. So that's just simply a long-winded way of saying I can take a look at what the print of, well, what the heck this range is. And if I go and it's say range, it says it's a class range. And what it does is that range generates what it says in the tin, a range of values. If I print out range 5, it tells me range 0 to 5. Now, pretty much the way we do almost everything in computer science is with ranges is that I'm going to use mathematical notation here, is that we do it like this. And for range 5, it's like this. Range 0 to 5. And you may have seen this in your algebra courses, this notation, meaning that we include the 0, but exclude the 5. Now that seems weird that we have an includes on one side and excludes on the other, but there is actually a really ridiculously smart reason to do that. So since this is a range of natural numbers, of integers, right? We don't have to worry about the floating point numbers in between them, of which there are an infinite number. This range consists of the numbers, well, starting at 0, because we always like to count at 0, we start counting at 0 in programming. except for those blasphemous languages that don't and start with 1, MATLAB, 0, 1, 2, 3, 4. This is the range of numbers. 0, 1, 2, 3, 4. Up 0, up to, but not including 5, right? That's what this parentheses mean. So it goes up to, but does not include 5. Now, why would I bother this way? Now, the reason we bother with doing it this way is because it lets us know how long the range is when we do this inclusive exclusive. By taking the end and subtracting the beginning. 5 minus 0 is equal to 5. Thus, we have a range of 5 numbers. Okay? Which implies, right, and me saying that implies something else. I can do this. 2 to 5, range 2 to 5. Which if I print it out, it starts at 2, goes up to, but does not include 5. So that will be 2, 3, 4, right? Goes up to, but does not include 5. Make sense so far? So here I've given it 2 arguments. You can, if you don't give it anything, basically its default behavior is, you want to start at 0, okay? Which is so common that basically we made it that the Python developers made a collective decision to decide, hey, you don't need to put in 2 values. You can just put in 1, and we'll just assume you want to start at 0. Make sense? Because it's such a common behavior. So when you don't put anything in as your first number, you don't put in a starting value, and just put in an ending value, it's going to assume your starting value is 0, which is such a common behavior. It makes total sense to do that. So now going back to that whole inclusive exclusive range, well, 2, 5 gives us 2, 3, 4. Which is 5 minus 2 values, which gives us 3. So I don't even have to run it or really think too hard about how many values there's going to be. It's 5 minus 2. There's going to be 3 values. This will run 3 times. All that's changed by this is, and same with this. Now the values have changed, but the number of times it will run has not, right? It will be 3, 4, 5 this amount of time. Okay. So now for the most part, even today, we're just going to be using something like this, where I put in some number. I will warn you, however, that it does take time to print stuff out, right? Printing is actually a fairly time-consuming behavior. So printing something 1,000 times can cause you to wait. Worst case scenario, you will probably have to kill the program, because if you like put in a couple million or something and decide to print out every one of those numbers, it will take a while to run. Make sense? So just be aware of that. So, okay. So now that we have a 4, and by the way, I can also put anything I want in here, which is I can put in a variable. And that's typically what we do. We typically put in a value and we say, say value is equal to whatever we want to print out. So value is equal to 5. And then this would be 0 up to, but not including 5, right? It goes up to, but does not include. And you'll be we'll be using the up to and not include whenever we deal with lists and slicing and strings and slicing and all sorts of other things. I think there's like one exception for that rule, and that's generating random numbers, where the entire range is considered. But that is another story. All right, so let us talk about pi. Okay, unfortunately, not the juicy, delicious type, which under normal circumstances, I might be tempted to bake a bunch of pies and bring them into class. But alas, with COVID, I think I might get into some trouble with that. But rather we are talking about pi, which is an irrational number, okay? Pi is an irrational number, which means that you can't really represent it as a fraction, okay? What is pi? Pi, okay, first, and just an aside here, Wikipedia is an amazing resource, believe it or not, especially on mathematical topics, okay? Because and the reason for this is that people go through the trouble to make these little amazing animations to kind of explain values. which I'll explain in just a second. However, there is one reason, there is a pretty good reason not to, why, there is a very concrete reason as to why you do not cite Wikipedia when you're writing academic papers. Any takers on why that is? And it's not the reason you're thinking. Yes. I mean, anybody could make anything. So Wikipedia is actually fairly robust in correcting some errors, although it does take years to kind of clear out certain errors that are collectively believed. Yes. Secondhand, you're getting there. Yes. Now, everybody, I mean, anybody can edit anything. Yes. Yeah.
Like it's already quoting amongst other sources.
Yeah, it's a tertiary source, not secondary. It's tertiary. It's a tertiary source. So meaning it compiles information about from primary and secondhand sources, which is when you're writing academic articles, you want primary or secondary sources. Primary sources being the source itself, or secondary sources, which are articles about that primary source. Tertiary sources are like encyclopedias and dictionaries, which are meant to compile this kind of information for easy digestion. There is at least as far as I understand it. That seems to be a silly reason, in my opinion. It just happens to look unprofessional, though, because of the reason that anybody can edit it. But in general, these are good, and I'm sure you all know the trick of going into an article and looking at the footnotes to start your search on a particular topic. Which, you know, get used to using Google Scholar. I personally find that to be you know, a much more robust way of actually doing research because of that. Also, it's kind of annoying once you get to certain levels, because then you're not allowed to edit certain Wikipedia articles because you are experts on them, and it's your original research. We've had that issue. So anyway, pi. So pi is the ratio of the diameter to the circumference, right? Remember, circumference is equal to 2 pi r, or circumference is equal to pi times the diameter, right? That's what 2r is. 2r is the diameter. So that simply means is that basically that if we take this this circle with that is one diameter that is a length 1 diameter, okay, it has a length 1 diameter, and we unroll it, then we're going to get, then when we finish unrolling it, we're going to end up with pi. That is a graphical way to express it, and I do enjoy that graphical way of expressing it. But mathematically, it's just simply the ratio between the diameter and the circumference. Now it's an irrational number. That means you can't represent it as you cannot completely represent it as a fraction, meaning that it kind of has an infinite length of precision. There's an infinite number of digits. But that doesn't mean that people haven't tried to approximate it before. There are a number of approximations of pi, because how in the world were you to calculate it? And the precision at which we have been able to get closer and closer values of pi, the number of digits, the level of precision we've been able to calculate pi at has just climbed over the recent years. One common thing, according to some Egyptologists, have claimed that ancient Egyptians used the approximation of pi of 22/7, which, if we calculate that using this side, 22 divided by 7, which allows me to talk directly to the Python interpreter, gives us 3.1428. So those first 3 digits are correct, 3.14. But 28 is not, right? Okay, but hey, in math, you were taught, like when you were initially taught geometry, you were taught pi is equal to 3.14, because in that level of computation, that level of exercises, that's really all the digits you need. And that's what it comes down to, just like our circle exercise from Tuesday, right? We couldn't draw a perfect circle, but we didn't need to. We just had to make it so that it looked like a circle, right? Similarly, we didn't need a perfect calculation of pi. We just need one that worked well enough. But people like to get better and more accurate information, okay? And various religious texts do mention different values of pi. based on the approximation and ease of calculation. Archimedes has his own calculation. I'm particularly fond of this Chinese mathematicians, or some of the ones that Chinese mathematicians came up, like this one. 355 divided by 113 is approximately equal to 5. And if we test that out, 355 divided by 113. Sorry, what was it? Was it 113? I'm down myself now. 113, which is 3.1459. That's pretty close. I mean, at that point, I mean, you've got 3.1415. That's enough. That's more than enough for a lot of things, especially with the kind of scale of technology. You're not getting down onto a really minute scale. We're building up giant circles. So that's a perfectly valid value, you know. But how in the world do you calculate these kinds of things? And the answer is we use something called approximation algorithms, which started getting developed in around the Middle Ages. We call them this used to be called, in some textbooks, this is called the Leibniz series, but it was pointed out that it's been pointed out that Madhava of Sangamagrama, which this is new information to me, was found to have done it more. And this is a common case where basically that we find that somebody who the original function was named for was not actually the first person to come out with it, right? Because, you know, mathematical ideas, you got multiple people around the world working on it and recording it, different recordings possibly being burnt or destroyed in disasters or routes, you know? And so, you know, information is gained, lost, and regained. That just happens. And then we live in an age where basically because of the internet, that's much less likely to happen. So the Leibniz formula was this pretty interesting formula. It's what we call a converging series, which we'll learn about in calculus 2, which simply says that we have this series of numbers that follows a pattern. And if we follow, and the longer we continue this pattern, the closer we get to this answer. So this is 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, so on and so forth. And the more numbers we add and add and add to this, the closer we're going to get to pi over 4. Now, so we can get, and how do you get pi from pi over 4? You just multiply by 4. So let's look at our target value for a second. Pi over 4. First off, I'm going to import math, which just simply tells, hey, math, I'd like the knowledge, right? Because I have a bunch of math functions that I normally don't need, like sine or cosine. If you need, you can I think this works, help, yeah, math, where you can basically ask, hey, what's inside of it? And it squeeze it up, but there's ton, and it lists everything else. But honestly, it's so much easier to just simply, you know, go onto your internet browser and go math Python, and there we go, docs, and go to the documentation website itself, right? And that has a list of all the things, including factorial, greatest common denominators, all sorts of things that are useful math functions. But anyway, let's go ahead and figure out what the value of pi is. Sorry, the value. So let's go ahead and see what the stored value of pi is. Math.pi, which is 3.141592653589793. Now, as I mentioned earlier, this is in no way possible all the digits of pi, but floating point numbers have a limit. So floating point numbers can hold 64 bits of information, 64 binary digits, which means that there's a theoretical minimum and maximum, but not only that, there's only so many significant digits, a term that you may still scar you from chemistry or biology. There's only so many significant digits that it can hold, which is this many. Furthermore, there's also minor imperfections from translating floating point numbers from decimal to binary into decimal again. But what do I mean by that? Well, for instance, 1.0 plus 2.0 gives you the result you would expect, but 0.1 plus 0.2 gives you a number that's quite unexpected, which is almost 3.0, but it's like, but there's like an atomically small difference between the correct answer and the answer it gives, just due to rounding errors and the fact that we're converting from decimal to binary. This is an oversimplified explanation. But suffice to say, there is no infinite amount of information to store all this because pi is infinite. We cannot store all of it. So we just simply store it within the limits we have because that is more than good enough for pretty much all the purposes we need. So with that being said, what is pi over 4 about equal to? It's about equal to 0.78. So let's take a look at that Leibniz function, that Leibniz formula again, okay? That Leibniz formula says, hey, the more we do this, the closer we're going to get to pi, right? So let's start with the first term, 1. Sorry, to pi over 4. Well, that's pretty far away, 1 and 0.78. I mean, okay, if we're talking like the difference between 1 and a million, that 0.78 is not that much of a difference between 1, but you know. So now we do 1 minus 1/3. Okay, and actually the absolute difference will get smaller. And then 1 minus 1/3 plus 1/5. So that's gonna, so this is getting, so that's certainly closer than 1 was. Okay, so 1 minus 1/5 plus 1/3 minus 1/7. And so now you can see that we're slowly closing in on 0.78, right? Very slowly. As we add, that's what this means when we say this, when we say this term, oh my God, look at that hair. I mean, that is some hair. I mean, okay, so anyway, moving on. But basically what it's saying is that the more terms we add, the closer we get to pi over 4. And if we could continue this all the way to infinity, we'd actually get pi over 4. We can't continue to infinity. But that's actually not too much of a problem because again, we can only store so many digits of pi in our computer, right? Also, but at the same time, like calculating this is a pain, right? Like me doing this manually is a bit of a pain, which is ostensibly how these people kind of figured that out and experimentally verified it, right? But fortunately, we have computers and mechanical computers, because electronic computers, not human computers, which used to be a job, an old job for calculating numbers. So first, let's ascertain the pattern. Let's make sure we've got the pattern. It's 1 minus 1/3 plus 1/5 minus 1/7, 9th. So what would the next one be? An 11th, right? It's 1, 3, 5, 7, 9, 11. So it's going up by 2 each time. Make sense? Okay. So it's going up by 2 each time. So what we want to do is that, so first, so we're going to start there before we try adding anything. Let's just try to calculate the appropriate denominators and print them out. Print out 1, 3, 5, 7, 9, 11, so forth, right? Just work on that thing. Because right now, if I tried to do this all at once, you'd probably revolt. And rightly so, because that would be unfair. That's trying to get from A to Z just by without explaining any of the intervening points. Okay? So let's go ahead and create a value called the denominator. Just to start out, and I'm going to just call it 1, and we may have to delete this later as I make this more as I iterate through it. But what we're going to want to do is that let's go ahead and I'll create a something called num terms. So the amount of, in other words, the amount of values I want to print out, right? The amount of values I would like to print out is, I'd like to do 10 of these, right? So, and just a note on syntax, by the way, a note on syntax in Python. There are basically 2 ways to do to kind of make a variable that's made of 2 numbers. One of those ways is the camel case that I'm doing. A camel case variable has humps. That you see, it's got the capital letters create humps in the variable, which allow you to read it. Okay, make sense? That's camel case. Okay, that's the way I prefer. It's the way done in Java, but it's not the way that is quote unquote Pythonic. But because I'm the one teaching the class and it's so much easier for me to type, that's the way I prefer to do it. The other way, which is using underscores. So like this, use underscores to split up words. So now it's all one variable, right? Which way is the correct way? Well, technically in Python, the way to do it is this way to do it. But you notice that I don't do it this way. That's fine. I actually don't care which way you use, so long as you're consistent. Don't mix and match, right? If you're going to use camel case all the way through in your program. If you use underscores, use underscores all the way through. Why don't mix and match? Because then you're going to get into trouble trying to remember, wait a second, did I camel case this variable or did I undercase? Or you might not even think that and camel case when you actually undercased when you underscored earlier, right? You know what I'm saying? So use one to keep it consistent. Yes. Yep, just naming variables. It's an important thing that's worth mentioning. All right, so we want to do 10 terms. All right, and we have our denominator, right? Which right now, if we just simply, so we want to print out 10 denominators. Actually, let's go ahead and bring this down to 5 because it's easier, because we can kind of do groupings of numbers and recognize a number of lines, you know, all at once and count them all at once. And 5 is kind of in that range that you can kind of intuit that that is 5. But like, so if I ask you to visualize 5, you can visualize 5 pretty easily. If I ask you to visualize 10, though, you're probably not going to visualize 10. You're going to visualize 2 5s. That's what I'm getting down to. So it's the matter of how easy it is to recognize a number is a number. Okay, so if I run this, it's going to print out 5 times, and the denominator is 1. But what we want is 1, 3, 5, 7, 9. So how can I change? What is a way I can go about changing this? Yes. Yes, I could increment by 2. There's actually multiple correct answers, and that is one of them, which is you can increment by 2. It's one of the 2 answers I was expecting. Denominator is equal to the denominator, which honestly is a bit wordy. So maybe I should just call it the lower term, which is much easier to type, much easier to say. The denominator, it's the lower term. Is 1. So now what we can do is we can say it's the value that it was plus 2. Okay, which will print out, and this is my mistake, not your mistake, by the way, which will print out 3, 5, 7, 9, 11. But what did I want? I wanted 1, 3, 5, 7, 9, right? So what can I change to make it instead 1, 3, 5, 7, 9? Yes? I could do that. That's one way. It's a bit of a roundabout way, but sure, it works. And I saw via hand motion the answer over there. Sorry, I did not mean to do negative 11, but that certainly illustrates the point. The other thing that I saw suggested by a student via simple hand motion is just flip the term, flip the lines around. So print out the value, then increment. This was a deliberate mistake I introduced, not one that was suggested by the student. And that's my story, and I'm sticking to it. Totally not an oversight on my part. Okay. So, and in chat, we do have one other suggestion, which is possibly the most correct one, and the one that I instinctively think of. Okay, so let me comment this out. And the one suggested in chat is the one that is probably the hardest to get your head around. But once you start programming, it is the one I like, which is print lower term times, so lower term plus 2 times who the what now? Right? Who the what now? How in the heavens did that work? Right? So the answer is the way this worked is that is what we've got here is that we have a number of terms, right? In fact, I can just simply replace this with 1 plus 2i because I'm not ever modifying that value. 1 plus 2 times I. So remember, what is num terms? Range num terms gives us a range from 0 up to and including 5. So how did this work? We got 0, 1, 2, 3, and 4, right? Those are the numbers. And each time we go through the for loop, we get a different value. The first time we go through the for loop, we get 0. The second time we get 1. The third time we get 2. Or perhaps the best way to think about it is that the 0th time we go through and get the value 0. And the first time we get 1, and the second time we get 2. Use whatever modality you think is makes most sense for your brain, because that would come. Because honestly, that's the most important thing, right? So here we start at 0. So we print out. So I begins by starting at 0. So we print out, and here I will print out I, and here we can see I, and this. So we print out 1 plus 2 times 0, which is 1. Then I is equal to 1. So we print out 1 plus 2 times 1, which is 2. 2 plus 2 times 2, which is 5. 3, then I is equal to 3, which means that we do 1 plus 6, and then 4, which gives us 1 plus 8, which gives us 9. And then finally, we are done with all of the things in our range, which gives us the end of the loop. And I can increase the number of terms and get more terms this way. So we've got the bottom of our denominator now. So we could print out. Also 1 divided by. Yeah. So let's go. Yeah. And why not just call it denominator? Like I said, you're allowed to be, assuming I spelled it right, which is always a hazard, right? Let's make sure and I almost certainly misspelled it because again, I got my PhD in computer science, not English. Oh, hey, I did spell it right, not bad. Okay, so then I can print out the denominator. Okay, the numerator is not hard because that's always 1, right? Denominator divided by, so sorry, 1 divided by the denominator. And there. So all I've done is just stored the 1 plus 2 times I in denominator. Then I print out the I value, the denominator, and 1 divided by the denominator, right? Which is going to become an increasingly smaller and smaller value, right? Because this is, for instance, this number is 1/39. So we've got the values for the denominator, which is a pretty good first step, to be honest, because we've got 1, 3, 5, 7, 9. All right, so the next thing I want to do is that we notice that the signs are flipping. The flipping signs are flipping, okay? So we've got positive, negative, positive, negative, positive, negative. All right, so how do we turn a positive, so in general, like on paper, what do I have to do to turn a positive number into a negative one? Yes? Yeah, multiply by -1, okay? Yeah, that's how you get a negative number. You just multiply by -1, okay? And how do I turn a negative number into a positive number? Multiply by -1. It's wonderful that it's the same answer. Very convenient, because if it wasn't the same answer, boy, would we be in trouble. So the negative number, so multiplying by -1 is how we can turn a positive number into a negative number. So ostensibly, if we just what we can do here is that we can set up a sign value, right? And start it at 1 or whatever. And then what we can do is that we can keep multiplying it by -1 to kind of flip it. So what we can do is that we could say, hey, so and that what we do over here, and what we just simply would do for the value is that we would do sine times 1 over the denominator, right? So right now it's all positive because I'm not changing anything, right? Common mistake I always make, and you'll constantly make, is that you'll create a variable and then you'll forget to do something about it, right? Because you were so fast in the thinking of it that you forgot to have the doing of it. So in other words, what we need to do is that we want to do sine So over here, if we do sine is equal to sine times, and here's another deliberate mistake on my part. So what I'll do is I'll say sine times -1, and that's, we'll get -1, positive 1/3, -1/5, positive 1/7. Oh, wait, that is the reverse. There you see, it's my deliberate mistake, right? I've got a negative, I'm going negative, positive, negative, positive, negative, positive, right? And what I wanted to do was positive, negative, positive, negative, positive, negative. So how can I change my code to fix that? Yes. Yep, totally could do that. I can totally, yep, there's multiple ways to do this. I can set the initial term to -1. Another way to do that is only change the sign after I've calculated the value and I'm ready to move on, right? Which you prefer is completely up to you. Both are valid. And again, it just simply matters as to which matches you're thinking the best. And since I do all the modification in here, I think I will just simply, put that there, saying, get ready for the next one. And so I have 1, -1/3, 2, a 10th, -7th, positive 9th, -11th. All right. Yes. I would think so. The module operator, you really want to use that for remainders or for chopping off all the preceding digits. Mod 2. Okay, yeah, but using an if statement, but that would require using an if statement. And I don't want to use any if statements. Right? Yes. Can I write in? No, I unfortunately cannot write in fraction form. Well, I can cheat kind of. I can cheat and make it write in fraction form by saying, hey, let's do, here's how I can kind of cheat to do that, which is that I will take this and I'll turn the denominator into a string. Okay. And then what I'll do is I will say 1 divided by, and I'll put that in strings. So that will, what that will do, so here, rather than seeing 1, you'll see 1/1. And it's easier to show if I show it this way. Wait, unexpected indent. Oh no. So important thing to know about Python. Aha. So what was my mistake? Where's my mistake here? Yes. Yeah, this is, I accidentally hit a key and somehow got a random 5 after the colon, which led to a, wait a second, what? There's an, so the way indentations work is for Python is that when it sees a colon, it immediately expects that you want to go to the next line. But if it sees a colon and you don't go to the next line, it's like, oh, whatever. That colon must be there for other reasons. And then it sees the indent and it's like, why is there an indent there? You weren't at an indent line ending. You were at an indent, you were at just a line ending. Yeah, there was a colon somewhere else. So colon line ending. There's a colon somewhere else, but. So anyway, going on to this. So there, I can print it out in a fraction form by basically saying do 1 over the denominator and print out the 1, the over, and then again, the reason I have to convert this is the one annoyance I have with Python. I have a lot of annoyances with Java, but this is like the big one for me in Python, which is that if I try to add a string and a integer in Java, which is the other language I teach in, the string, it says, oh, you want to add a string to anything else, then obviously you want to convert the thing you're adding to the string to a string. But Python doesn't do that. It says, hey, strings in this type can't be added. So you have to convert what you're trying to use into a string if you want to connect it to that string like that. But as we can see, we've got our fraction now. And now we can actually do, if we wanted to, we could do, in reality, what we should do is do that and now plus, and now do sign, str sign, which is really just 1 or -1, but we're calling it sign because it functionally acts like that. And now we've got our proper fraction, right? 1 over 1/3, 1 over 1, -1/3, +1/5, -1/7, 1/9, and so on and so forth, right? Okay, so now we're going to just move it. We're gonna just pause here and move on and just take a step back on another theoretical kind of, not theoretical thing, but the other last piece, which is that we need to add them all together, right? We need to add them all together into a into a sum. So I want to just move aside and just work on that in a more generalized case before we, sorry, a simpler example before we bring it into this example. Because this is another common pattern we have, which is called the accumulator pattern, where we just accumulate a value. So because Python is very good at adding up numbers. Now, when we're adding up numbers and we're adding a bunch of them together, you might be tempted to call it sum, and that would be perfect in other languages, but sum, as you note, and sum, it's hominin, yeah, word that sounds like it. You notice that it's different color here, right? This is because sum is a built-in function for adding together a bunch of things. For instance, I could do, there's a lot, once you know the workings of the inner commands, you can do a lot of cool things, like sum of the range of let's see, 5 to 105 by, yeah, you can add a third value to range, by the way, and that means by what step? And, oh, right, no, that won't work. And then you've got to print it out. So you can do this, which isn't god-awful big statement, which once you understand, which once you're comfortable with isn't so bad, but just beginning looks pretty bad. That is 1050. And what did this do? Well, range 5, 105, and 5. So here, right, the way you read that one, by the way, for range is start at 5, go up to, but don't include 105. By 5s. So I'm not, so the range isn't 5, 6, 7, 8, 9, 10. It's 5, 10, 15, 20, 25, 30, 35, 40. That's what that last one means. Okay. So it just happened. So, and then sum just simply said, hey, you're generating this range of numbers. Can I just add them all up all at once? And that's what sum does. It does exactly what it says on the 10. So sum is a built-in function, but if you proceed to use it, there's nothing stopping you from doing this, by the way. Print sum is equal to 6. Print sum. There's nothing that stops you from doing this in Python, by the way. So you can totally call your variable sum, store a number inside of it, but once you do so, you've kind of not overridden, but overshadowed the original function, preventing you from using it in your current program. Yeah, I mean, you're not going to permanently damage your computer forever or anything like that, or permanently damage Python. It's just literally for the sake of the program you're currently running, you cannot use that sum function. So just keep that in mind when you see purple variables. Yes?
What happens if you made some local variable like a function, but it's still like that number?
I'll be honest, I don't know. I think like instinctively, I'd like to say that that if you made it a local variable inside of a function, that it wouldn't override it. But with Python, I'm not 100% sure. I'm just not 100% sure. Like I'd have to test it out, that kind of thing. So, I mean, regardless, it's considered harmful. Don't do it because it would be a bad idea because you want that thing. So in general, when you see me using, instead of using sum, you're going to see me using the word total a lot in Python when I want to add things together. So total is, so the accumulator pattern works something like this. For number in range, whatever my range is, 5 in this case, total is equal to total plus number. And here, what I'm going to do is I'm going to make this a bit easier, and I'm going to say it's 1 to 6. So it's going to be 1, but up to, but not including 5, which is the numbers 1 through 5. Sorry, 1 through 6, which is 1 up to, but not including 6, which is 1, 2, 3, 4, 5. So we're just going to add in 5 numbers here. 1, 2, 3, 4, 5. Okay, so this adds in the numbers 1, 2, 3, 4, 5. And the hardest part of this is right now we have this self-modifying statement over here, right? In math terms, right? Saying in math terms, generally saying x is equal to x plus 1 makes no kind of sense. It generally says, generally when that happens, it's like you're saying 1 is equal to 2. You broke math. Congratulations. Do not go directly to jail. Do not pass start. You know, generally a bad move. But remember, the equal sign, even though I keep saying equals, it's not the it's not equals. Equals just happens to be two syllables in English, so I use it a lot. Because what's happening here is that I am assigning the value. Assigning the value. So 6 syllables. You know, so right here, I'd be saying, hey, take the value of x, add 1 to it, and store that value in x. So here with total, what I'm saying is, hey, currently you've got 0. And number is equal to 1. So take 0 plus 1 and store that in total. And total now becomes 1. Okay, and then the next step, it says, hey, you've got total, which is now 1, and I've got this number, which is the next number is 2. So take 1 plus 2, compute it, just 3, and now store it in this variable. So now total stores 3, right? We evaluate the expression on the right, and we store it in the variable on the left. That is always the order of things. You evaluate, and then you store, which is why this works. So if I now print total, it will be 1 plus 2 plus 3 plus 4 plus 5. And what I find funny, what I find completely reasonable, but still very funny. So this is 15, 1 plus 2 plus 3 plus 4 plus 5. That makes sense because, let's see, 4 plus 3 is equal to 7, and 1 plus 2 is equal to 3, 7 plus 3 is equal to 10, 10 plus 5 is equal to 15, right? So totally reasonable. What I find totally reasonable and interesting is that there's a shortcut for this because it's such a common operation, which is plus equals. You plus equals the amount you want. So in this case, so for instance, if I did total, if I said x is equal to 5 and then said x plus equals 6, x's value would now be 11 because I just incremented the value by, this means change the value in x by 6. Although it is in reality the same statement as what I had before, which is x is equal to x plus 6. The same statement. It's just this, for some reason, is more readable to a lot of us. Okay, but for here, what I would do is, so here I would just simply saying rather than a specific number, a literal number, I'm going to use the variable number. And that 11 is coming from here. So the way the accumulator pattern works is as follows. let me go ahead and move this. And let's see, how do I comment things out at all at once in this? Comment out region, Alt 3, nice. Okay. So we see that so the accumulator pattern works like this. Set up some value to store your numbers in. Okay, to add your numbers in. We then do a for loop, and each step of the for loop, or formally each iteration of the for loop, that's what an iteration is, a single step in the for loop. Each step, let's add that number to the total. Make sense? So here, what I'm going to do is I'm going to add this number to the total. And then when I'm done, I'm going to print out that total. That is the accumulator pattern. And I call it a pattern because we see it a lot. You're going to be using it a lot. You're going to be doing it a lot in homework 4. Now, I should mention before you get too freaked out that everything I'm talking about here and introducing here gets reintroduced again in your lecture, in your book, and your lecture videos for next week's stuff. It's just that next week's stuff is is so important that I devote a lot of time to it. This week's assignment is just going to be familiarizing yourself with the turtles a bit more, and you don't need for loops for it. That said, if you find it easier to use your for loops, go ahead and do it. Go ahead and use for loops. Yes. Sorry? The second quiz will be over for turtles and for loops. The first quiz is over chapter 2 and stuff covered in lab 2 and basically creating equations. By the way, that quiz, if you didn't see the announcement, is due tomorrow. If you need some more time on it, like the due date is too soon, let me know. I can always push that back. But in general, if you see that you get a poor score on it, you most likely didn't. It most likely means that the auto grader either broke at some point, or other times it will report it as not completely correct. Also, I found out that it does automatically submit your answers after the time limit goes out. So if you have an extended need for time, let me know about it. In future, what I'll do is I will create a time. I will leave it untimed in the future, so as not to cause that issue again. But I'm still discussing with my TAs the best way to handle quizzes, but because of the possible flux of people in and out of labs and not being able to come in person to do the quizzes, and there being so many of you, the bulk of your quizzes will be take home and online, right? It worked out last semester just fine, but there will be some that we will be doing in person, but not quite yet. And those, just like anything else, those will be announced. You will know about them in advance. They will be very simple questions, such as here's a program, a turtle program. What is the draw? What does it draw? And the answer is you draw a triangle, right? Something like simple like that. Make sense? It's not going to be, they're going to be those kind of exams, sorry, not exams, like quizzes will be short and closed notes, and they're just really to make sure that we understand that you actually do understand what's going on and that there aren't some shenanigans going on with the online exams. So it's more data for us. Okay, so anyway, accumulator patterns. So this is the way it works. We just simply keep increasing it by this number. So we increase total by 1, then we increase it by 2, then we increase it by 3, then we increase it by 4, then we increase it by 5. Remember, this is just a fancy way of writing this, right? Okay, so now that we've got that going out, by the way, with these three quotation marks in a row, this has 2 functions in Python. The first is a multi-line string. In other words, this is just one big string. But because I'm creating a big string literal that I'm not assigning it to a variable or anything, and it's just happening in the middle, and it's just in the middle of the text, it effectively acts as a multi-line comment. So that's useful, meaning that the computer is just going to read it and ignore it. So, okay, so now what we need to do is that we need to do our accumulator pattern. So I'll create total here is equal to 0. And I'm going to just follow the same exact pattern here. I calculate the denominator. And then I'll say, what is the term that we are adding? The term is equal to sine time, and it's going to be this thing, sine divided by the denominator, right? What I was printing, and that's just what I'm printing out over here, did the denominator, sure. And then I will do total plus equals term. And that's really all there is to it, right? I could also just do, right, because here I'm just taking the contingent parts and doing this. I could just as easily have done this, by the way, where he said, hey, add this instead. But it made more sense to me to break it out into a separate line to do, right? So here I say, hey, here's the denominator. Okay, now the actual term, the 1, the 1/3, the 1/5, the 1/10, 1/7, that is 1 over the denominator, or -1 over the denominator, right? So I store it in that value, and then I'm going to add that to total. And then I'll print it out and flip the sign for the next variable. And so print total. And that gives me and doing it 20 times gives me these values, which gives me 0.77. Now I can go ahead and comment this out because again, printing is going to take time. And the value I'm aiming for is pi though, but this gives me pi over 4, remember? This entire thing doesn't calculate pi, it calculates pi over 4. So if I want to figure out if I'm getting close to pi, what I'm going to do is multiply this by 4. And then what I'll do over here is I will just make sure I'm getting close to the answer. I will go to the top, import math, and then I'll just simply have print out my approximation, comma, math dot pi over, let's say math dot pi. So multiply by, so now if I run this, on the left is our term and on the right is there. And we get 3.09 versus 3.14, which isn't that great, right? If I was doing 22/7, at least I'd have 3.14, right? But here, I'm only doing 20 terms. So why don't I up the amount of times I'm doing this? That's what this variable allows me to do. So I'll up this to 100. And now I'm at 3.13. 15. Although interestingly enough, we've got 3.13159, 3.14159. That's mildly amusing. That it's off in the places of lower accuracy. That's correct on the places of lower accuracy. So now let me go ahead and do this. So I did this. It was pretty quick. So if I run it at so I just did 100. If I do 1,000 times, how much longer is it going to take to compute this? 10 times longer because I just multiplied it by a factor of 10, right? But fortunately, that's basically nothing for a computer, which now it's computed 3.1405. So I'd have to add a total of 1,000 terms in order to do this, right? That's a lot of handwriting. So good thing we didn't try to do this by hand. We'd be in the night, and then 10,000. And notice that even though it's taking 10 times longer, that's basically nothing for a modern computer. The modern computer is a number crunching, mean adding machine. 100,000 of these, still not even blinking, and we're getting closer. 3.15, sorry, 3.1415, 3.1415, 8, 9, getting closer. And so let's add another multiple of 10. So now we're going to compute this 1,000,000 times. Oops, sorry, 1,000,000. But the reason I keep hitting 5 is that I keep going up to here to hit F5, and I accidentally hit 5 while I'm hitting F5. Because F5 is the keyboard shortcut for run. And now we notice that it actually took a bit with when we went for 1,000,000, when we went for, is it 1,000,000 or did I up it to 10 million accidentally? Yeah, I accidentally upped it to 10 million. 10 million times. So it actually did take a bit of a, oof, that was a bit. But now we've got 3.1415925 versus 19.6. And now, again, if I up it by a factor of 10, I'll be talking and it's still going to be running because it takes 10 times as long. It's going to just take a bit for it. Not like forever, right? Algorithms have a beginning and a specific ending. It's just going to take time, unfortunately. So reading any good books lately? Yes.
How do we like stop the code? It's like,
That's not a book.
still
Yeah, sorry. How do you stop the code if it's still running? That's an excellent question. So there's a couple ways to do that. The first is try to hit this X button. Okay. So let's go ahead, but let's go ahead and experiment with that. I'm gonna run. It's going too long. I'm worried I've written what's a common programming error, which is called an infinite loop. So hit this. Your program is still running. Do you want to kill it? Yes. I'm merciless. And that will stop. And that will stop it. Another thing you can do is you can also go over to here, and you can select and you can say interrupt execution. This is another common thing where you can hit Control C and it will just, notice what it did. Gave me, this is an error. I literally just hit a keyboard combination that made it crash, which is a built-in feature in a lot here where I can just hit the keyboard combination and make it crash if I need to. It's called a keyboard interrupt. In fact, we see, let's see, open in Windows Terminal. In 1 second. So open settings. Yes. Okay, this is gonna, you know what? This is going to be appearance. Come on. I'm just trying to make it so that's easier to see. Color schemes. Okay. From this PowerShell, do I have appearance? Oh, there we go. Let's go and up the font size to 32. So here I'm working in the shell, right? Which is just kind of the basic way of talking to your computer. So here I am in my desktop, and I'm going to use the Python command. If I turn off, and I'm going to say, hey, run this program that I have called the Py-in4. And you'll see, right, this is the one that's running, that's taking forever to run, right? So again, that keyboard execute keyboard thing comes in handy there, where you press Control C or possibly Command C on a Mac, and it just automatically crashes it. Okay. Worst case scenario though, you can always kill the window that it's trying to work in. Okay. And then if you need to, you can bring out the big guns on a Linux system. That should be, sorry, on a Linux or a Unix-based system like a Mac. Use xkill as a command, which just simply says, hey, point me at a window and I'm going to crash it. I'm just going to crash it. Or on Windows, you can just like go to your task manager. You can do the same thing on a Mac. But your only real concern for an infinite loop that you can't control, that you can't close is if you accidentally write or download or run a wabbit. A wabbit, or also known as a fork bomb. Which is our first piece of malware that we'll talk about here. It's one of the oldest and most basic kinds because it doesn't really do anything much in terms of damage other than denial of service. Example of the fork bomb in many, you can write the fork bomb in many languages. In fact, in Python, it's as follows. While one, meaning do this while true, while true, meaning while forever. Do this forever. Operating system, call the operating system, then tell the operating system to fork this program. What does fork mean? It means create a duplicate of this program and run it. So while this program is running, create a copy of this and run it, which will then proceed to create a copy of itself, whose copies will copy it themselves and copies will copy themselves. So the original program is still making copies of itself. The idea behind here is that it completely overwhelms any other resources in your system such that it cannot run. Now, of course, how do you solve such an issue? You pull the plug, right? Or you try to, because when a program is forked, you may not just be able to exit out of those processes because those processes could be independent. But it's common enough. I mean, worst case scenario, again, you just simply have to wait until the computer runs out of battery, or you got to pull the plug on the server and reboot it, which is really only a big concern if you're running a big server. It's actually, and these are really the only ones that you can't really just kind of just, you know, kill, I think. But I mean, once you reboot the computer, it's all fine. So, but anyway, going back to this, we see that basically, so what we've done today is that we've worked on the Leibniz formula for pi, right? Okay, or the Madhava-Leibniz formula. And what we've done is that we did this, we calculated, we had this equation, and as we added an additional, and as we added more and more of terms of this pattern, as we continued this pattern on, we got closer and closer to pi, right? We got pretty close at 10 million. And there's a number of advanced proofs as to why this works. It's scary calculus with squiggles. And honestly, a lot of calculus and math is just meant to look scary and intimidating. Like this would be less scary if it was actually the word sum as opposed to a sigma. Like the Greek makes it all scary. Yes. Well, I didn't have it print 10 million times. I just had it print once at the end. If I had it print 10 million times, it would take forever, right? I mean, we're still in the 2 digits, right? Yeah, so printing out takes a long time. A long, long time. Hence why I've just killed the program. Or at least it goes, actually the printing does go quicker if you're not working in idle. It's just idle has very slow printing, but even then, here I'll show, I will show and tell. Right, even then, if I'm not working in idle, printing does take a non-trivial amount of time. Okay. Oh, CD, sorry, wasn't in the right place, CD desktop. Now I can, now that I'm on, right, see, it's going much quicker outside of idle. Idle prints very, very slowly. But here it's just printing as fast as it can. But as fast as it can, it's still pretty slow. I'm in the hundreds of thousands.
Is that this space? Is it proper? Like
it's as fast.
Printing, and this is working in the background. That total move that fast or fast?
It would move faster because it takes some time to render it on screen. And not only do I have to render it on screen, but every time I print a line, I have to move these. I have to buffer it and move everything out of the way and stuff like that. It takes time to print stuff out. Normally, a trivial amount of time.
Not turn it off. Put it run in the background. Or...
Probably, yeah. I would assume it would run in the background since I'm telling it to print. But like if I do this, it will take. And there are ways to time the runtime of programs. Printing does take time, but it's also like not something to worry about unless you're running a loop that is going to run 10 million times. Make sense? All right. So, right, your first quiz is due. Your second online quiz will be posted next week, but again, that's when it's going to be posted. It will probably be due somewhere around week 5. Okay, that quiz will deal with for loops and turtles, which are things we've only just started to learn about. Again, and lab 4 is all about for loops, and it's all about for loops and turtles. So it's got like 2 separate parts where you work on for loops and turtles. If it looks like you get a poor score on the exam, don't worry about it until Saturday evening. I'll have the grades posted for the exam, for those quizzes on Saturday evening, most likely, Sunday at the latest. You won't have an accurate score until I run the grader and release the grades. Okay. Yes. I will not be able to take demos because we unfortunately do have a class right after this. What I will be doing is I will be altering my office hours for Tuesday. Starting next week, I'll be moving them to hopefully be a block in the evening rather than a block in the morning. That way that I can meet with students at a completely different time.
All right, thank you.
Sorry about that.
No worries.
I just had a question.
Yep.
For on Runestone, my grade went down to 75, but when I click on the readings, it says like that, and then all this.
So weird. Okay.
Wait, is that like it gives you 75 and it's like over 100?
Yeah, it's like 160.
All right. I'm gonna run. Okay.
It's not changing it, right? Yeah.
That's cool. I'm gonna go ahead and let me give me a second. Okay, and let me stop this program So stop sharing. All right, see you, everybody.